Hello everyone, welcome to this week's Crunch seminar. Today we have two speakers. The first speaker is Yinling Zhang. She will be presenting her work on a causality-based learning approach for system identification and data assimilation of complex dynamical systems and applications. Yinling is a PhD candidate in mathematics at the University of Wisconsin-Madison under the supervision of Professor Nan Chen. She holds a master's degree from University of Wisconsin-Madison and a bachelor's degree from Shanghai Jiaotong University. Yinling's research focuses on physics-informed machine learning for complex dynamical systems with expertise in stochastic modeling, data assimilation, and uncertainty quantification. Her interdisciplinary work spans material science, fluid dynamics, and climate science applications. Yinling has been recognized with several awards, including the John Noel Award from the Math Department at University of Wisconsin-Madison. She has presented her research at many applied math and interdisciplinary conferences, including AGU, SIAM, and EGU meetings. With this short introduction, I would like to invite Yinling to present her work.
Yeah, thanks for having me at Crunch Seminar today. I'm excited to share my research about a causality-based learning approach for system identification and data simulation. So we are trying to figure out how to discover underlying dynamics from the partial observation, and then we use discovered model for real-time forecasting. So before I get into technical details, I want to introduce my advisor and main collaborators. And first, my advisor Nan Chen, who is an expert in applied math at UW-Madison. He works on uncertainty quantification, data simulation, machine learning in Earth system, information theory, and mathematical modeling. And the work I present today has applications in different areas, so we've been collaborating with the experts in each field. For the climate science direction, we work with Jerome Wieland. He is a leading climate scientist in ANSO and ocean dynamics, and he helped us with the ANSO applications, in which I will show later. And for the material science, we collaborate with the Kurt Bronkhorst, also here at the UW-Madison, formerly from the Los Alamos National Lab. He is a material scientist working on the polycrystal mechanism, and he provides us with many insights about the computational material model. So here is what I will cover today. First, I will introduce the motivation, why this problem matters, and what challenges we are trying to solve. And second, I will walk you throughout our methodology, how we use the causal inference in model discovery, and then integrate it with the data simulation. And then after that, I will show a proof of conceptual example to demonstrate how the method works. And finally, I will show the real-world applications in the climate and material science. So first is the motivation. Complex turbulent dynamical systems appear in many areas such as geophysics, neuroscience, engineering, and climate science. These complex systems are characterized by strong nonlinearity, high dimensionality, multiscale structures, and we usually only have the partial observations. Despite these challenges, we have two fundamental goals. First, we want to make the reliable predictions. It requires good models. And second, we want to use the observations to improve the predictions. That's what we call data simulation. And because we are under partial observation, we also want to recover the full state estimations. So to achieve these goals, we need two key capabilities. First, to identify the model, we want to discover the underlying dynamics from data. And second, we need efficient data simulation. We incorporate the observations for real-time forecasting, or we want to recover the latent variables. So traditionally, we have two kinds of method to modeling complex systems. First, the physics-based models, which is built from the first principles. It always has the good interpretability and is built based on the strong physical understanding. But it's always requires strong assumptions and can be computationally expensive, such as numerical weather predictions. And the second one is the data-driven method, and it even works when we don't know the governing equations, and it could be very computationally efficient, and but it lacks the interpretability and requires the large amounts of data. So the data simulation is at the intersection. It combines the data with existing models and to recover complete information and reduced uncertainty. As new observations become available, data simulation can use this information to improve the real-time prediction. So let's talk about the data simulation using the observations for the real-time forecasting. For the linear Gaussian case, we have the classic Kalman filter, but the real-world systems are really linear or Gaussian, so there are many efforts to tackle the non-Gaussianity, such as ensemble Kalman filter, full-dimensional variational method, particle filter, and the conditional Gaussian filter. This method is what we will use in our framework. So data simulation typically works in scenarios where the observations are partial and noisy. And there are several challenges. So first, we have the nonlinearity in the system dynamics and non-Gaussianity in property distributions. And it could be computationally expensive due to the high dimensionality. And we also have the model uncertainty and the parameter estimation issues. So this brings us to a fundamental question. We need a good model for the efficient data simulation, but we also need the good enough data to identify a good model through the machine learning methods. So how do we combine them together? There are different methods to combine machine learning for the data and the data simulation. So on the one side, machine learning for data simulation, machine learning can serve as the cheap surrogate models to generate ensembles, or using machine learning to estimate the error covariance statistics. And people always also use the purely data-driven end-to-end data simulation, and or for the model error corrections. And on the other side, data simulation for machine learning, the data simulation can provide with better training data, and it also corrects the machine learning model predictions. And there are also methods like ensemble Kalman inversion to use the data simulation for the derivative-free optimization. So So what we want to do is to make the machine learning and data simulation interact each other in a loop continuously, and they can help each other get better results. So in our framework, there are three key components. First, iterative data enrichment. We incorporate data simulation to generate samples to recover unobserved components in machine learning training because we are under partial observation. It provides us with a more complete and dynamical consistent dataset. And second, the model update. The NERD model acts as a surrogate of the physical system. It's providing the improved model outputs for the data simulation. And finally, once the identified dynamics is identified, data simulation method can be applied again to correct the state estimation and improve forecasting skill. So the key idea here is that the machine learning and data simulation are not separate components, but iteratively and mutually reinforce the process. And there is another important component in the model identification is the causal inference. To build accurate models, we need to know which terms are truly important in the system. It's not straightforward because even terms with small coefficients could be dynamically important. The existing method applies the L1 norm regularization, but it could be computationally expensive when dealing with the high dimensional system and struggle with the high correlated terms. So our goal is to identify a computationally efficient, robust to noise and interpretable and physically interpretable method to identify the complex systems. So we introduced the causal inference. The challenge here is when the physical laws are unknown, how do we extract meaningful information from data? So the causal inference quantifies the cause and effects relationships between variables. It goes beyond correlation to identify direct influence. It determines which variables truly drive the system dynamics. And it's also important for building predictive models from sparse observations. So the key question is, which candidate functions actually contribute information to the system's evolution? The causal inference could give us the answer. So we used information theoretic method here to measure unique information of each candidate's function and account for nonlinear dependence between state variables. And it systematically identify causal structure from data alone. So the next section is the methodology. Unlike the traditional physics-based modeling or the purely data-driven method, we use causation entropy to incorporate physics into an efficient data-driven method. And so we use the causal inference to detect the relationship between the candidate's functions and the state variable evolution, and to handle model error and uncertainty quantification. We include a set of cheap but powerful stochastic process as the latent variable in the system. We call it the stochastic parameterization. So here is the overview diagram for the causality-based learning algorithm. On the left-hand side, we have the available information. We are under partial observation. In this example, we can observe the time series for x1, x2, and y1, y2 are hidden variables. And we also create a library of candidate functions. It includes the combinations of the state variables. And there are three key components in the learning algorithm. First, we start from the conditional sampling because we are under partial observation. So we need to use the conditional sampling to sample the trajectories of these hidden variables. And then we trace the sampled trajectories as artificial observation. Then we can use the causal inference to determine the model structure. We determine which terms should be kept in the systems, and in the third component, we estimate the coefficients of selected functions via a simple maximum likelihood estimation. Once we have the model structure and the parameters, we have a new complete model. Then we can use this new model to update the trajectories of hidden variables. Then we can continue this loop until we get the convergence results. So we can incorporate physics constraint and localization to deal with the high dimensional system. And this method is computationally efficient because we have the closed analytical formula throughout. So let me introduce these components in details, starting from the conditional sampling. We assume our system fits into this conditional Gaussian framework. And here we have the observed state variable x and unobserved state variable y. So y is linear given the x, but overall the equation for y could be highly nonlinear. So given this conditional Gaussian structure, we can have the closed analytical formula to sample the trajectory of y. That could significantly reduce the computational cost. So here are the formulas. We have the equations for mean and the covariance evolution. The conditional sampling is based on the Bayesian framework. We are using data assimilation method to estimate what the unobserved state variable look like, given our observed state variable x. So one thing I want to clarify is the goal of this stochastic parameterization. We are not trying to recover the exact dynamics of the unobserved state variables. What we are trying to do is to recover the statistic feedback from the unobserved variable y to the observed variable x. So we don't need to know exactly what the unobserved state variable y is doing at every moment. We just need to know how y statistically influence x. This makes the problem much more tractable. And it turns out that many
Can I ask a question, Yinling? Can you go back? But
Yeah.
you have in the first two equation 2a, you have for x, you need y of t. So you're saying that you will have y of t, but it will not be accurate. Only its statistics will be accurate.
For the observed state variable, we know the trajectories of them, so we can accurately model the observed state variables. But for the hidden variables, we don't know the trajectory, so we actually don't know if we can exactly capture the time series of it. So here we want to capture the statistic feedback from y to x.
Right, but what I'm saying is you're not using the statistics of y. in obtaining x. Finally, when you reconstruct the whole thing, right, you're using y of t, which is instantaneous.
Yeah, so we assume our system fits this conditional Gaussian structure, and we want to have a full state estimation.
Isn't that a strong assumption? That's what I'm asking.
Sorry?
Isn't it a very strong assumption?
Actually, because this many complex nonlinear system has already fits into frameworks, so yeah, it's based on this assumption, but it still keeps the nonlinearity of the whole system, so it's not a very strong assumption, I think.
Okay, all right, thank you. Please
Yeah.
proceed.
Yeah. So it turns out many complex nonlinear systems have already fit into this framework, such as the physics constraints nonlinear stochastic models and the stochastically coupled reaction diffusion models in neuroscience and ecology, and the multiscale models in turbulence and geophysics flows. So in the next component is the causal inference. Here we have the state variable z. It includes observed state variable x and unobserved state variable y. And here is the general framework of our model. Fi is the candidate's function from the entire function library, and theta here is the coefficient matrix to be estimated. The goal in this step is to determine the non-zero entries of this coefficients matrix. So here we introduce the causation entropy. The causation entropy is defined as follows. It measures if Fm has the information contribution to Zn, and we compute it by computing the difference between two conditional entropy. H here is the conditional entropy, measures the uncertainty in x given y. So the condition of the first term here is the entire function library accepts the Fm, and the second condition is the entire function library. So if the result is close to 0, it means that the Fm doesn't have the information contribution to Zn, or the information contribution could be replaced by other candidate functions because it doesn't matter if we have Fm or not. And if the result is greater than 0, it means that the candidate function Fm has the causal inference. So it measures the unique information contributed by the candidate functions, and it accounts for the nonlinear relationships for the candidate functions. So the challenge here is the computational of the causation entropy suffers high dimensionality. So we use the Gaussian approximation to solve it. And here is the equation for the Gaussian approximation for the causation entropy. Here, Rx is the covariance matrix of variable x, y, and similar for the other terms. So there are several advantages. So first, computational efficiency. It enables rapid determination of the sparse matrix structure without complex high-dimensional integration. And here we only approximate the distribution using the first two moments during the post-processing. So it keeps the nonlinearity. And it also have the reliable identification. It can successfully identify the significant causal relationship even when the true distribution is highly non-Gaussian. And the third step is parameter estimation. We estimate parameters via a simple maximum likelihood estimation. It's straightforward. And in this step, we can incorporate the physics constraints together with other constraints through this formula. Here, the H and G are constants matrix. And to incorporate these constraints, we use the Lagrangian multiplier method. So once the model is identified via the causality-based learning algorithm, data assimilation serves as multiple importance roles. So first, it assimilates the real-time observations to correct the model predictions, and it also provides the probabilistic forecast with unquantified uncertainty. And it also tests whether identified dynamics captured true system behavior. And it could help us to evaluate model performance under different case or different conditions. And third, it could also validate model across different spatial and temporal scales and help us to assess the model robustness with varying observation densities. So this is really important because it's closed loop. We are not just discovering models and hoping it work. We're actually testing them in realistic forecasting scenarios. The data simulation process tells us whether our discovered model is useful for real-world applications. And then I will show a proof of concept example. So this causality-based learning algorithm successfully identified many complex high-dimensional systems. And here we test it on a two-layer Lorentz 96 model. This is commonly used as a test for data simulation and parameterization in the numerical weather forecasting. And here is the equations. And UI is the large-scale variable. And it's the observed state variable in this system. And Vij represents the small-scale variables. So, and Vij is the hidden variables in this case. And it's a high-dimensional system. Here, the capital I denotes the total number of large-scale variables, and the capital J is the number of the small-scale variables corresponding to each large-scale variable. Here is the model structure of this two layer, and we can see we have the Vi, which is the large-scale variable, and each UI have the several Vij's. And for the convenience of discussing the behavior of two layers, we introduce the Wi, which is the sum of the Vij for each UI. It describes the total variabilities in the second layer. It's because in practice we don't know the interaction between the hidden variable itself. What we want is the feedback from the hidden variables to the observed variables. And based on this simplification, we have built the candidate function libraries. And because this is a high dimensional system, we use the localization here, which means for each observed state variable UI, we have built a candidate function, including the adjacent state variables, such as ui minus 1, ui minus 2, ui plus 1, ui plus 2, and the quadratic combinations of them. And for the hidden variables, we also have some terms in the function libraries. So here is a simple example for how we visualize the coefficients matrix. In the top parts, we have some sampled equations, and we extract the coefficients matrix from these equations and visualize the coefficients matrix by the heat map. The different colors represents the coefficients of the functions in the model. And in the panel D, we have the coefficients. It shows the coefficients matrix of our initial guess for the Lorentz 96 model. So it shows the results for our causality-based learning algorithm. In the panel A, we have the true signals, and in the panel B is the initial guess. We can say that it's totally different from the true signals and far away from these behaviors. But after several iterations, our identified model could capture the similar behavior as the truth, and the coefficients matrix also close to the true coefficients matrix. In the panel D and panel E, it shows the Bayer truncated model and the Bayer truncated model with re-estimated parameters. We can say this bad performance imply the importance of stochastic parameterizations. So in this test, the causality-based learning algorithm successfully identified the model of this Lorentz 96.
Yinling, I have a question because it looks to me that the identified model and the truth, U, is very different. Why you say so the prediction is very inaccurate. If you do an pointwise errors or the errors are very big. Just with the naked eye, I can tell.
So here is the model simulations, and we don't use the same random seed, and so we just compare it in so we just say if this can produce the similar behavior. We can say in the initial guess it's totally different, and
No, I know, but the fact that it goes closer to the truth, it does make it correct. Are you trying to? I still don't understand. Are you trying to predict U instantaneously and reconstruct it together with all the parameter estimation, or are you trying to predict statistics, same statistics for U?
yes. So currently we're trying to predict statistics, and if we apply data, here is just a model simulation. If we apply the data simulation here, we will compare it. We will try to predict the this observed state variable U. Then we will get much closer results to the truth. But here we just identify a model that's close to the true model, and we separately generate the model simulation. So
this is is this only the causal inference part? You haven't used the data here to assimilate, or you have?
yeah, so it's the results of the causality-based learning algorithm. So we have, we use this discovered model to generate the model simulation to say if we can capture the statistics of the truth.
So this is like the first step, let's say, of the process.
Yeah, so I will show the data simulation results in the later applications.
Okay. Thanks.
Yeah, thanks for the questions. And so in the next section, I will show the real-world complexity in climates and the material size. So our first application is the ANSO modeling. So what's the ANSO? ANSO stands for the El Nino Southern Oscillation. It's alternating the warming and the cooling of the sea surface temperature in the Pacific Ocean. During the El Nino events, the Eastern Pacific getting warmer than the normal, and during the La Nina events, the it gets colder. So ANSO is one of the most important climate phenomena. And the challenge is that capturing ANSO complexity is important to understanding the different types of the El Nino events. Some El Nino are strong, some are weak, and some happens in the Western Pacific, some happens in the Central Pacific, some happens in the Eastern Pacific. So the different types of the events have the different impacts. And we also want to know what's the minimal model for the ANSO complexity. We want to know what's the least number of state variables that can still capture the ANSO complexity and diversity. And we also want to which nonlinear arrays in the ANSO modeling is important for extreme events. And we will also want to use data assimilation to validate the discovered model. So here we apply the causation entropy to identify the key dynamical terms, and it's systematically derived hierarchy of stochastic models, and we can test our models through the integrated data assimilation. So in the ANSO modeling, we have several state variables. U represents the zonal ocean currents. HW here means the thermocline dips in the Western Pacific. Tau represents the wind burst in the Western Pacific. And the TC/TE, they are the sea surface temperature in the Central Pacific and Eastern Pacific. So this is the data assimilation results for a hierarchy of stochastic model that's identified from the Causality-Based learning algorithm. In the left-hand side, we have the data assimilation results. We designed 2 experiments. So in the first experiment, we can TC and TE are observed state variables. We try to recover the remaining state variables in the identified model. And in the second experiment, we treat the TC and TE as unobserved variables and we want to see if the identified model could recover the TC and TE's time series. And the right-hand side, we have the correlation results between the recovered time series and the observations. We can see that among these identified models, only this 3-dimensional model has a low correlation. So this includes the 3 state variables, HW, TC, and TE. And in order to find the minimal model, so we will conduct another test to say how to identify the minimal model. So here is the results that we incorporate a latent variable in that 3-dimensional model. we use the data assimilation to recover the full state estimation, so here the HWTCTE, they are the observed states variables, and we found that the behavior of latent states variable is like the wind burst, which is an intraseasonal variable. So is implied, and this four-dimensional system can capture the answer complexity. In the model simulation, we can say it's reproduce many different types of the answer events, such as the extreme EP or Nino events, CP or Nino events, and some multi-year events. So it implies that if we want to have a minimal model to capture the answer diversity, we need at least these three interannual states variables and one intraseasonal states variables, and it's also captured the importance nonlinearity for extreme events reproduction. So here we use the conditional Gaussian structure to enable the efficient data simulation. So the data simulation we use here has two important roles. First is help us to correct the model prediction, like in our first results. It could help us to do the real-time correction using the sparse observation, and it also provides us with the probabilistic forecast with uncertainty quantification. And in the second dynamical test, we validate the and it also help us to validate the model across different answer phases and test the extreme events predicting capability. And by adding a latent state variable, the data simulation also helps us to say what the latent variable represents dynamically. So in general, it demonstrates a unified framework integrating the interpretable model discovery and operational data simulation for climate prediction. And for the second application is the material science. The critical problem is that the damage in polycrystal material often starts at the grain boundaries, and understanding the internal stress distribution at grain boundaries is important for damage prediction, and it can also help us to guide the material design. And this figure shows the predictions from the simulated polycrystals. And we can see the red shows the high stress regions. And there are several challenges in the existing method. So first, full-field crystal simulation are computationally expensive, so it's difficult to run them many times and have a statistic estimation. And her tau region stress distribution are often non-Gaussian. And third, causal relationships between microstructure features and the maximum stress remain unidentified. So our goal of this work is to identify the causal relationship between the microstructure features and the minimum and maximum stress. And we also want to have a statistic model to achieve the computational efficiency. And our data comes from the simulations from different crystal configurations. And we progress from the simple to complex structures. And we start from the single crystal and to the bicrystal with 2 orientations and to the quad crystal with 4 orientations and finally the octocrystal with 8 orientations. And we can classify the microstructures into 2 categories. The first is the elastic properties. It includes the green orientations, elastic constants, and elastic strings. And the second category is the plastic deformation. It includes the dislocation density, non-Schmidt factors, plastic deformation rates, eigenvalues, and eigenvectors. So finally, we will identify a model using these different microstructure features to predict the states of the maximum stress. And here is the results for our statistic model. So panel A shows the PDFs of the identified statistically resulting model. Here, the red line shows the true stress, and we can say it's a strong non-Gaussian. And the black line shows the PDFs of the residue, which will compute the difference between the predicted stress value and the true stress. We can say the variance is greatly reduced and is close to the Gaussian distribution. It means that the identified model could capture the most non-Gaussian properties. And for the accurate prediction, we also include a method to quantify the uncertainty of our predicted results. So for each predict stress, we have a conditional distribution. And we can say the conditional distributions accurately align with the true values, which is shown in the dashed lines. So here is the summary. In the methodology part, we use the causation entropy method for identifying the causal relationships in the complex systems. And we use the conditional Gaussian structure enable the analytical data simulation formulations. And we use this iterative machine learning and data simulation framework with mutual reinforcement. And we also incorporate the physics constraints and the uncertainty quantification. For the applications, we can successfully model the answer complexity and systematical derive the minimal interpretable model for answer. And for the material science, we can have the non-Gaussian stress prediction in the polycrystal systems. So it demonstrates the improvements in both model discovery and the forecasting skill. So in general, it provides the interpretable models for the real-time data simulation, and it's also bridged the gap between physics discovery and operational applications. Yeah, that's all. Thank you for the listening, and here is the reference papers.
Thank
Thank you
Yinling.
so much.
Thank you, Yinling, for presenting your work. We can now open the floor for questions. If anyone has questions for Yinling.
Hi, Yinling.
Hi.
I'm a PhD student at Brown. I had a quick question. So could you comment about how the computational cost of your method scales with the number of variables or the dimension of the problem? Like, for example, if you're just doing ensemble Kalman filter, you have to invert a D by D matrix, right? So do you have to do any matrix inversions or something? Like, how does the computational cost scale?
Do you mean in our method how
Right,
the
right.
computational cost for the data simulation?
Right.
Yeah, so because in here I can, yeah. So here we have the equations for the mean and the covariance at each time. So we have the equation here. So based on the model and the observed state variable x, we can directly sample the trajectories of the hidden variables, and we don't need to generate the ensembles to compute the mean and covariance of them. So because here we have closed analytical formula, so it's a computational efficient method.
Okay, so what's the shape of like B1 transpose? Because that's the matrix you need to invert, right? Is that D by D? Like, is that like if X is
Yeah, so so it's based on the trajectories of the observed state variables and also based on the models here.
okay.
So in the conditional sampling method, conditional sampling step, we need to have an initial guess for this model. We need to first have a guess for this functions A0, A1,
Okay.
something like that. Then we can do the conditional sampling.
I see. Okay. And also like does the method require that X is linear in Y? Like so here it's given X, it's like conditionally linear in Y, right? So if you have like A1X plus Y square or something, if you have a nonlinear term in Y.
So you mean if the Y itself is nonlinear?
Oh,
So
yeah. If it's just if it's non-linear, yeah.
and so because it has an assumption for this stochastic parameterization structure. So for the X, it could be arbitrary nonlinear, but for the Y, it's conditional linear because actually if the X is given, the Y is linear. So if for the case that's not suit for this structure, we so on the one side we can, because it's a approximation for the hidden variables, we don't want the hidden variables has the very complex structure. And on the other side, if we still want to have this no, actually for this model structure, we still keep the nonlinearity of the whole system. And on the other side, if we still want to have the nonlinearity for the Y's equation, we have another version of the work that involves the Koopman operator.
Oh, okay.
Or
All right.
solve this kind of problems.
Okay. All right. Okay. Thank you.
Yeah. Thanks for the questions.
Thank you.
Thank you, Alan. Do we have more questions for the speaker? I have a question, actually, Yinling. For the ENSO model and the polycrystalline problems, how would you quantify the goodness of your predictions? Like, what error metric would you use? Do you have a quantification of the prediction quality?
So in the answer applications,
Yes, for example, here, how would you define the error metric? What error metric did you use to quantify the errors?
So in this work, we identify a hierarchy of stochastic models. So do you mean how to determine which state variables should be determined in each model?
All right. I think my question was more relevant for the polycrystalline case, I guess. The next test problem. What is so you're trying to predict something, right? You predicted the extreme values of the stresses and you showed the error of the distribution. But what if you want a single number to represent the quality of prediction? What would that metric be?
So in this case, we have the time series from the observation, or we have the from a reference simulation. So it means that we have the time series for all the 6 variables.
Right.
Yeah.
Now you're going to
So
use like a mean squared error. What error do you use as notice?
and actually here do you mean how do we conduct the prediction of the answer models? Or so here we actually in this test we use the ensemble common filter, so we can choose which variables is observed variables and which variables is the unobserved variables, and then we recover the trajectories of them with the uncertainty quantification. Does that answer your question?
Partially. Yes, sure. Okay. Thank you.
Yeah.
Do we have any more questions for the speaker? If not, I would like to thank Yinling again for taking her time to present the work, and maybe we could move on to the next talk.
Thank you so much.
Thank you, Yinling. Hi, Kai. Can you try sharing your screen?
Hello. Oh,
Hi.
is it my turn? All right. Do you want to wait for maybe 2 or
No, I think we are good. We have enough people in the audience. If you could share your screen.
all right? Because I don't see Themis yet. I think he's joining.
Okay.
I hope he's joining.
All right.
Maybe he is.
Maybe give me a second. George, is it all right to continue or should we wait?
Yes, please
What's up?
continue.
Oh,
Yeah.
Sorry, I didn't get that, George. Sorry.
Yes.
Okay.
Continue. Please continue.
All right. All right. I'll just introduce you first. Give me a minute. And so for the second talk, Kai Chang will be presenting his work on extreme event-aware eta learning. And Kai is a third-year PhD student in the computational science at MIT, working with Professor Themis Sapsis. Before MIT, he served his undergraduate degree from Emory University. With the short introduction, I'd like to invite you to present your work. Thank you.
All right. Thank you, Vivek, for the kind introduction, and thank you for having me. It's a great pleasure to give a talk at this venue. I will tell you something about something we call extreme event aware or eta learning, which is really a statistical framework for modeling extreme events, in particular in the context of dynamical systems. And this talk is generously supported by Department of Defense or War and the Air Force Office. And it's a joint work with my advisor, Themis. I hope he's joining today with us later. So let me just give you some motivations through examples, right? Extreme events, these are the events that happen very irregularly, meaning that with low probability. And when they happen, they induce significant consequences. Some examples would be extreme climate scenario, thinking about something like tornadoes, tsunamis, engineering systems, finance, stock market. You see time series, there are dynamics there. Chemistry, chemical processes, and pandemics, and more generally, biological processes. So these are the real world examples. So obviously, trying to understand extreme events has a lot of value in there because there are so many applications. But mathematically, what do we mean by extreme events? So in this talk, throughout this talk, this is the setup we are looking at. Imagine we have some input space or input random variable to start with. And X, a random variable, we assume it takes value in a d-dimensional Euclidean space. We also assume it follows a distribution mu that is tractable by assumption. Here, what we mean by tractable is either we can draw as many samples of X from mu as possible, or we can we just have already had enough samples so that we can approximate mu with very high confidence. And the input random variable is then mapped into the state space through a mapping U. You can think about a state as, all the things you need to know to characterize the situation right now that you care about. And U in general is very high dimensional and it is unknown. This is very tough to, to get a good understanding of it. And then the states are mapped through a mapping G into the observable space. Importantly, we assume the observable space is a one-dimensional, the observable takes values in a one-dimensional subset of the real line. And the form of G is typically assumed. What we mean by this is you give me a snapshot U, I can compute the observable G of U for you. And this is a pretty common setup in extreme events because you got to tell me what extreme means, right? Now, if we group our notation a little bit, if we call the composite map of G and U, we rename it as Y, and then there is a new random variable induced by this map, which we call capital Y, and by definition, this Y follows the distribution Y push forward mu. So this hashtag notation throughout the talk will mean the push forward. Then the task is really, many things are already assumed in this setup. So we really want to build an estimator for the high dimensional mapping U. But this is a hard task, right? Because it's high dimensional. In extreme events, there are two closely related, but kind of separate tasks in this that we can study. The first is maybe we want to capture the tail risk. This is the probability that your observable Y deviates beyond a threshold T star. T star is a constant that typically depends on your application. So this is, user picked. This is the tail risk. A harder task, I would argue, is to capture the risky scenarios. And what we mean by this is the risky scenarios are the state snapshots, or the states that induce the tail risk. So, these are the things that really happen under the hood. Why is this harder? Because in order to do this well, it amounts to have a very good understanding of the high dimensional map U. Because it's high dimensional, this is hard. For the purpose of our talk, we introduce we are looking at data-driven modeling in extreme events. And by that, we mean we are given something more, which is a data set. We're really looking at a supervised learning setup. We're very simple setup. Given a data set of xi, u of xi, and y of xi, given n triples of this kind of data points, we want to build an estimator for the true mapping U. And then we either want to capture the tail risk or we want to capture the risky scenarios. This is the game we are playing. For existing methods, there are many of them out there. Typically, the underlying assumption is that extreme events appear in the data set. And then with that assumption, you try to capture, the tail risk or the risky scenarios. And here we mean like it doesn't have to be a data-driven setting. Here, what we mean by extreme events appear in D is really, you have enough knowledge about extreme events so that you could say something intelligent about it. And for things like large deviation theory, you assume you know the equations the underlying equations. And for sampling-based methods, you always assume the sampling process sort of hits the extreme region so that you could estimate the tail probability or see the risky scenarios. This is all fine, right? Like it's already a very hard task, assuming the existence of extreme events appear in the data set or you have enough information about extreme events and try to do this is already very hard. But here we are really asking a different question. We're asking, what if you just genuinely don't have enough knowledge about it? What if your data set does not contain any extreme events? What if just, resource due to something like resource constraint, or what if the nature just does not allow you to see these things ahead of time? Then is there anything we can do about it? Apparently we think there is, and our thinking process eventually leads us to this framework, which we call eta-learning. And it's very simple. The thing we do is, well, since you don't have enough information, there's no magic, right? Like you got to give me something more. And the things that we are proposing to use here is an extra distributional information on the observable space. That is to say, we assume a distribution, or in many applications that I will show you, just the tail of the distribution will be enough. And we call this distribution nu zero. This is the a priori information that we are assuming. Then, we run the optimization problem, which we define as follows. This is a two-term optimization problem, very simple. The first term is it's just the least squares empirical risk minimization. But this is happening in the state space. The second term, which acts as a regularizer, is happening in the observable space. And this lambda here is a weighting parameter, a hyperparameter, which our method has shown to be pretty robust to. And the regularizer is a W1, a one Wasserstein distance, which I show you briefly the definition here, between the push forward of the composition of G and your estimator phi. This phi is something you think of it as a neural network. This is something that you want to pick from, like try to estimate your map U. So this is the push forward. This is the one Wasserstein distance between the push forward and the a priori distribution nu zero. That's pretty much it. Like if I stop there, that would be the talk, one-liner. But then if you have followed throughout the talk so far, you might have a lot of questions at this point. You might ask, what about the availability of nu zero? How can we, how is nu zero available? In what situations are nu zero available? If it is not available, what can we do about it? While this is not the focus of this work, I will briefly comment on it. And more importantly, what do we mean by data scarcity, right? Like what do we even mean by extreme events here? And then why W1? Why not, doing something like KL divergence? Why not W2? Why not WP? Why not Hellinger distance? Like there's so many things you can put there. Then why W1? So we have some mathematical theory here, and I will show you. So before getting to the next part of the talk, is there any questions so far?
Yes. Kai, can you give us a scenario about this, what you call the risky scenarios? Because just give me one example, let's say with winds or something, any physical example to get my
Absolutely.
head around that. Yeah.
Absolutely. You can think about maybe a wave equation, and you can think about like each time step as a state. And the risky scenarios, the observable, you can think of it as a supreme norm or something. And when the supreme norm of each snapshot deviates, that typically indicates you probably have a huge wave on the space or something. And that huge wave is the things that we really want to understand. And that is what we call, as an example, risky scenario.
Okay, so it's sort of mathematical. It has mathematical connotation, not physical. I thought it was some sort of physical connotation.
I mean, the example I gave was a physical example. But mathematically it means, it means a large
So
deviation.
G is what? G is a functional.
G is a functional, yes. G is a
G is a
functional
functional of the state of
of
those
the
in the snapshot, right?
state, yes.
Okay, so it could be anything basically.
It could be anything. So the setup is pretty general. And but yeah, of course we have very specific applications later on.
But then you take a difference with nu naught, because
Yes.
nu naught is the tail of the PDF of the state.
No, nu naught is the tail of the observable. That's the
Oh,
important.
okay, of the observer. So now you observe the risky, the functional.
Yes, we observe we assume a distribution on the observable, and then we want to work our way backwards.
Okay. So
Yeah.
if it's not the state that you observe, it's something else, but you have new knot for that.
Yes, this new knot is something we assume. Yeah.
Okay, great, thanks.
Yeah, of course. Any other questions? All right, if there's no further question at this point, I will move on. First, I want to comment on the availability of new knot. And it's a very brief comment. There have been a lot of works in the past in asymptotic methods that trying to do asymptotic analysis of stochastic dynamics. And for many of those works, they are you can arrive at a asymptotic distribution of new knot. Sorry, of the observable. So you could use that from there. There's also a large deviation theory, which I forgot to put on there, because in our method, we only assume the tail, and large deviation tells you, is the mathematical field, is the probabilistic field, like trying to understand the tail. But then, of course, like you can say these are not dramatically accurate for many of the times, but you could have this information. So yeah. And the second thing that is probably like more and more, or increasingly more relevant these days, is you might have a pool of unlabeled data that you cannot use for your supervised learning. And with that, with that unlabeled data, since you cannot use it for supervised learning, but you could probably do like unsupervised learning to get an estimate of the distribution, of the observable distribution. And then with that information, you could inject that into the iter-learning framework. So in that sense, iter-learning is also a sort of a bridge between supervised learning and unsupervised learning. And the third thing is more general, which is you could just like throw in a hypothesis, or you could call it oracle, and then try to see with that hypothesis what iter-learning or any other methods can generate those risky scenarios for you. So this hypothesis setting is very relevant in things like climate change. So in climate change, maybe people, climate scientists might have a very good understanding of how the climate will shift, but then in the end, you want to understand what the climate scenarios look like on the Earth. So yeah, that's the brief comment about new knot, or yeah. And next, I want to move on to a little bit of mathematics. This will be a little bit more technical than what we had before. So this is the roadmap. We will first focus on a class of estimators that we argue are meaningful to the problem we are studying. And then we will try to show that this class struggles to capture extremes when the data set is small. And we will have a quantitative meaning of what small means. And then, after we show this is pretty obvious that, we need to do something to capture the extremes. And then we will argue that enforcing W1 matching actually works. And in the end, I will try to convince you that W1 is optimal, at least for this class of estimators. And we will define what optimality means. So let me just start with something we call data consistent estimators. And this is a class of estimators we're focusing on in the theoretical part of this talk. We let E be an extreme set. This is the set where your input takes values A, and your observable has a large deviation. And we assume this tail probability is upper bounded by a constant delta. And we say an estimator U psi of y, y psi of y. This y is it's the high dimensional to one dimensional map, is data consistent if either or both of 1 and 2 are true. What is 1 and 2? Why either and both? Like, this is pretty technical, but for one of the theorems, we need both of them to hold. But for the rest, we only need one of them to hold. So I just put everything here. Either or both one and true. One and two are true. What is 1 and 2? 1 and 2 says when none of your input data is in the extreme set, so you don't see any data in E, then the approximation error outside of E is the approximation error outside of E with the absolute value outside of the integral is at most the approximation error that's happening within the extreme set. So this is the, you could argue that, this E takes a small measure because it's extremes, but for theoretical purposes, this is our setup. And the second is just to move the absolute value within the integral. 1 and 2, like they don't necessarily imply each other. So that's data consistent estimators. And we would argue that, data consistent estimator is actually a very good candidate for us to study in this problem, because we want to study the scenarios that our method really overlook those extreme events. And here by overlook, we really mean we formalize this as the approximation error on the extreme set exceeds the approximation error on the non-extreme region. I hope that's intuitive. And theorem 1 we have is for a data consistent estimator in the sense of 1, with n is at most this number. This number is log p over log 1 minus delta, with probability at least, okay, I missed a p here. This p appearing in the numerator is the probability of this statement. With probability at least p, we get that the Wasserstein 1 distance between the true push forward and the estimated push forward is lower bounded by this value. And this value is dominated by the approximation error happening in the extreme region. So why is this useful, or why is this insightful? This is basically saying when the amount of data you're having in your data set is no bigger than certain number, then the push forward distribution is at least, or sorry, the Wasserstein distribution, the one Wasserstein distance, sorry, between the two push forward distributions is at least some number. Well, if you think about it, the distribution deviations in the tail, even if you can actually show this very rigorously, that if your Wasserstein 1 distance is, let's say, 0.0001, there's still a good chance of your tails suffering from, like, being far away from each other. You can actually show that by, constructing a mathematical example. So this tells us that data insufficiency, meaning that n is no bigger than some number, can actually result in very poor tail approximation. And here we emphasize can result in. So this is potentially result in. You can also cook up examples where the tail is very good, but then you have the bulk just deviating a little bit. That's also valid, but this just does not preclude you from having a poor tail approximation. That's what we are emphasizing. And this happens with probability at least p. And this eventually forms a motivation for our mathematical motivation for our method, because and this motivation is constructed in W1. And the second theorem I want to show you is to argue that enforcing W1 actually works. And the actual assumption we are throwing out here is this. This is to say the integration of the absolute difference between your estimator and the truth in the extreme region is upper bounded by some constant multiplied by the product of some constant, and this very same integral where you put the absolute value outside, and k is at least 1. The way to interpret this is well, if you think of if you look at this inequality backwards, so if you reverse the the less than or equal to greater than or equal to, and you let k equals to 1, this is universally true. Like you're just like making the you're just like putting the absolute value within the integral. That's universally true. So this backward condition is telling us that your estimator, when it misestimates the extreme events, it misestimates them on one side. So that when you do the integration without absolute value, the signed difference, they do not cancel with each other. So that's that's actually technically very important for the proof. And if you think about it, it actually intuitively makes sense because of the structure of W1, which I'm not getting into in this talk. So under this extra assumption, and that if y c is data consistent and satisfies this, under this assumption and the assumption that y c is data consistent, uniformly as this extra term that we enforce in our optimization problem goes to 0, then y c converges to y in probability. Now, this is a surprising truth. Why is it kind of surprising? Because typically when you enforce the distributional convergence, you can only, well, guarantee distributional convergence. But here we're saying distributional convergence, or rather convergence in W1, is equivalent to convergence in probability. So you could interpret this as a sort of central limit theorem or something. So yeah, so that I hope gives a argument about why enforcing W1 can work. But in practice, which I will explain further, this condition is rather difficult to enforce because you need this to uniformly hold as you need this assumption and the data consistent assumption to uniformly hold as you do the optimization. But the takeaway message here is if they are true, then convergence in probability is equivalent to convergence in W1. And this third theorem I want to show you is the optimality of W1. And this is the theorem where I say, well, we need to enforce both 1 and 2 to be true in the data consistent condition. So if this is true, if both 1 and 2 are true, under assumption 1, we can show that W1 between your estimator, W1 between the push forward distribution of your estimator and the true push forward distribution is lower bounded and upper bounded by some constants multiplied by the error in your extreme region, the approximation error in the extreme region. So this is pretty much desired in our application or in the framework, because in the end, we're interested in the tail errors. And this term is the tail approximation error in the observable space. So we claim that with this theorem, we can argue W1 is tail optimal for data consistent estimators. So that is the theoretical part. And I am not getting into the proof details in this talk because I want to leave some more time for discussion and questions. Is there any question at this point about the theory? If there are no questions, I will move on to applications. We have a lot of applications to show you here. The general protocols for the applications here is we assume the new knot is the truth. So we are doing proof of concept validations here. Assume we know the truth, the true distribution, the true observable distribution, except in the last example. And when we run the optimization, we use neural networks as our function approximators. And in the rest of the talk, when I say densities, I mean high fidelity kernel density estimators that have been validated very well. The first application is a two-dimensional to one-dimensional toy example. So there are no state maps here. There are no intermediate high-dimensional thing. And on the left, I'm showing you the truth. I'm simulating. So this contour is a true map. And the crosses here are the training data I'm assuming we have. So you see the true map here have different components. And the important thing is when we construct the training data, the extra peak on the lower right corner is left out. So this is to simulate the data scarcity situation we have been talking about earlier in the talk. And if you run this thing with mean squared loss, if you run neural network with mean squared error, you will get something like this, which makes sense. This thing leaves out this extra peak on the lower right corner because there's no data in there. But if you enforce the actual regularizer in the learning, you will get the eta learning estimator. And eta learning estimator, in the part where you do have enough data is approximated, not perfect, but okay. But the important thing is there's an extra peak showing up here. And this shows up because we have this actual regularizer. So this is the artifact of having this regularizer. But then you see this extra peak does not show up in the exact same position as our truth because this is distribution. What we are enforcing is a distributional convergence. Now you could ask, well, didn't you just tell me that when you enforce W1 distributional convergence is equivalent to convergence in probability? Well, that is true, but here without extra information, we cannot enforce the either the assumption one or the data consistent estimator condition to hold. But like if there is a way to enforce that, you will see probability convergence in probability. So this is distributional convergence.
So here, did you check which one of the one or two conditions is valid here? None of them?
That is a good question. I didn't really check numerically, but I would argue probably none of them would satisfy in this example.
Sorry, say it again.
Probably none of them is satisfied.
None of them. Okay.
Yeah. And then if you play this game again, mean that if you reinitialize your neural network, sorry, okay, this is the map, but then how do you validate this map is okay? Well, you look at the push-forward distribution. The push-forward distribution actually matches pretty well. The y-axis here is on the log scale. So when you see the push-forward of the MSE estimator, it looks fine, but it's in the log scale, so it's actually pretty off. And yeah. If you play this game again, meaning that you reinitialize your neural network and train this thing again, you will see that eta estimators every time it is aware of some peak out there, but every time it's gonna give you something a little bit more different. Why is this useful? Well, in many scenarios, in design engineering, well, I'm not really too familiar with that, but I'll quote what Themis said. In design, you probably want the statistical properties to hold in some sense, and this is especially true in climate change. So you want to have a statistical consistent manifestation of the scenarios, of the extreme scenarios. So yeah, so this is the intuition. And next, I want to move on to...
I have a question.
Yeah.
So I understand that you cannot pinpoint the third blob there at the location, but the blob looks much bigger than the actual size. Is that the conservative estimate?
Oh, you mean the eta estimator?
Yeah.
Okay. Yeah. Sorry, I forgot to add this. So here the input distribution I'm assuming is a isotropic Gaussian, a standard Gaussian. It's a standard Gaussian. So you have like the probability deviates as you move away from the center here. So 0, 0 is the center of the X distribution. So you have this bigger blob, but the actual density or the actual probability, the actual measure of this block is definitely the same as this thing here, because it is bigger, but it's also further away from the center of the Gaussian. That's why. If you plot the Push-Orr distribution for all of those cases, you will see an exact match in the tail.
But in the top left,
Yes.
for example, it's pretty close to the location, but still is big.
Well, if all I can say here is if you plot the input distribution, sorry, the output distribution, the push-forward distribution, they match. It's a pretty spot on match. So I would argue that's what's important. And I can't really, I really can't say. I agree. Like this looks a little bit bigger than this, but this also deviates. Like this also has like more mass in the tail part, in the further tail part.
That's my point. That it looks like it has more mass overall. So so it looks like a conservative estimate that that there is an extreme tail,
Yeah.
which is much bigger than actually is.
The
Maybe I
tail.
misinterpret that.
The tail here. So if you look at this thing, I promise you, if you plot the push-forward distribution of the whichever plot here, it will show a similar PDF as the red start one here. And the tail here is really this part. So this part is is the value when you are beyond, let's say, I don't know, like 0.45 or something. And of course, like the occurrence of those tails are probably centralized on here. And in the rest of these are the bulk of the distribution. So it's the value that determines whether it's the bulk or the tail, the value of this contour. So if
Okay, go ahead. Don't worry about it.
Yeah.
Thanks.
Yeah.
Hi, can I ask a question? This is Panos Tinis from Pacific Northwest National Lab.
Yeah.
What I see here for the different cases where you trained is that you get the main two blobs, and
Yes.
the other blob, the third one, is in different positions around the main two blobs. So what I was thinking was that this could be an artifact if you are using a kernel density estimator which is radially symmetric and it's isotropic, like you said, right? It doesn't take into account the angular position.
Oh, okay. When we do the computation,
Mhm.
meaning that when we compute the loss function, we don't need to use kernel density estimator. This is I didn't show it here, but in one dimension, W1 distance has a equivalent characterization, which is you integrate the quantile from 0 to 1. That gives you the absolute difference between the quantile function from 0 to 1. You get your W1. So here, when we do the optimization, that's actually the key thing in the numerical implementation here. You only need to basically you get the quantiles, you sort them, and you make the quantile align. So you don't
Exactly, but this is an alternative way of saying something along the same lines, that I think that in what you are doing, whether in your regularization, you should allow some kind of anisotropy there. Because what you are doing now with the quantiles is just too coarse, it's too blind to see the position that you could probably get. Because I think that if you get the two blobs, probably in them there is also some information about where the third blob is, where, not just that it is somewhere in the circle around them, but where. But if you only enforce the quantiles, this is statistical information, and probably it cannot be seen by the regularizer that you're using through W1. So this W1, I think, should be augmented somehow, this regularizer, with some notion of possible anisotropy there. Because I see that it's struggling to get it, and it says, oh, it's there, it's there, it's there, it's there. So if you look at it as distance from the other two blobs, it's more or less the same distance, but it's in different positions on a circle. So if it had some information that, to pinpoint the direction, and not just the distance from them, but the direction, it could maybe also get, the correct angle.
I have two responses to that.
Yeah.
The first is I do agree that if you enforce this sort of like information in this situation, you would get something. You probably would get this. Sure, like this is very struggling to get the truth, right? Like
Yeah.
But I do agree with you. If you have those extra information, that would be nice. That would be nice to enforce. But the second response I have is for this particular work, we are really not considering those actual information. So we are just trying to do. You could say this is an initial step in this line of work. That
Yeah.
But I do agree with you.
Yeah, because in the next slide, what is it, 21, you do get the tail right, for the observable. No, sorry, when was it? The other slide, this one, yes, 19, yes. You do get the tail right. So you are able to reproduce the statistical information, but when you turn it back into the actual density form, it doesn't get the correct position, but it gets the masses somehow right? How, the frequency of these events, but
Yes,
not
exactly.
where they come from. Yeah,
exactly. So in other words, to maybe rephrase your point a little bit is we don't really have spatial we don't have spatial consistency here.
exactly.
Don't enforce it.
You get statistical consistency because your regularizer works with quantiles, so
Yes,
it only
exactly.
sees probabilities. Yeah,
exactly.
Yeah.
That's
okay. Thank you.
Yeah, that's exactly the point of this this thing I'm showing. Yes.
Okay. Thanks.
I appreciate it. Thank you. Yeah. And next toy example I want to show you is just a little bit more complicated than the last one. This is when you do have the intermediate high dimensional. Well, by high here we mean 2-dimension, but it's a higher dimensional toy example than the last one. And the second dimension here acts as noise. So this is the random Fourier mode I just picked from Python random seed, and we keep the same situation. The data points are the same, and the first dimension of the intermediate state map is the same as the full map in the last example. And then because there's an actual noise in the second dimension, then extra dimension here, the MSC is learning this this first dimension a little bit off, and the eta estimator is also like the two blobs here. You're learning it a little bit off because of the noise in the second dimension, and then the key thing here is again like you do see the actual peak here, and if you plot the density, the push forward density, you get a pretty good match between this and between the eta density, eta push forward distribution, and the truth. And I want to emphasize, and I forgot to emphasize in the last example, when we do this optimization, when we try to do the quantile alignment, we only enforce the tail to match, meaning that all the bulk here is learned through the supervised learning loss in as a first term in the objective function. So that I just want to comment it out. Of course, you can play the same game, you retrain it or something, and you get different things, and they all have like pretty good statistics. But then again, like the spatial consistency, it's I would say it's a little bit you're relying on the power of PyTorch here. So and next, I want to show you a series of real world example. And this is in the context of precipitation modeling. And the task here is we want to build a map that, given a low resolution input state of your climate scenario, I will output to you a high resolution version of it. And in order to simulate this data scarcity in this example, we are assuming we only have very limited truth about the very limited information about the high resolution snapshots. So when we train this model, we are only using, in climate terminology, we're only using 0.5 years of pairs between the true low resolution and the true high resolution pairs. And I will show you how their statistics look like. You will see that the high resolution information we're using does not have the extremes. But yeah, but the task here is we want to infer the 25-year high resolution precipitation dynamics that contain unseen extremes. And we're assuming we have the true observable statistics. So the task here is, again, to align the observable statistics. And the results, I'm showing you 3 snapshots here. You can plot more. I'm showing you 3 of the tail snapshots in a sense. And the first row is a low resolution input. The second row is the high resolution truth. This is the ground truth. And the third row is the MSE. So you train this map with only 0.5 years paired data, input output, using the mean squared error. This is the inference you get for this particular LR input, for each of the particular LR input. And the fourth row is the eta learning, the output you get from eta learning. So yeah, that's that. You see 3 examples here, and in this, let's do it one by one, right? Like in the leftmost example, there is extreme in the truth, high resolution truth, and you see there's extreme in the eta learning output. But the spatial consistency is off because we only assume we have 0.5 years data, and the spatial consistency is, if you look at the shape, is sort of aligned with what you get from MSE. And in the second and third column, so the next 2 examples, you don't see as extreme in the high resolution truth, but in the eta learning estimator. Oh, by the way, in the first example, the MSE is is completely off, so you don't have the extremes here. And in the rest of the 2 examples, you do see extremes in the eta learning output, but the thing is, well, the LHR, the high resolution truth, it does not contain any extreme events. So this is expected. You can think of this as this extra peak that I have shown you in the Tau example. It's the high dimensional analog of that. Because we don't know exactly where, on which day does extreme show up. We only have a very how do I say, we don't have a statistical understanding of them. So when we force this, it could appear in the same day as the true extreme. It might not appear in the same day as the extreme. But the important thing is, if you plot the extreme statistics, you see a good match between the eta learning estimator and the truth. And the extra line here, compared to what we had before, the extra line, this is orange rhombus line. This is the training data, the statistics of the high resolution training data. So you see there's a cutoff here because you don't have the tail information, because we are only using 0.5 years. And when we do inference, we do inference on 25 years of data, input low resolution data. And next, I want to show you an application in generative modeling, which is, again, we have the same data set. We have the same setup where we have 0.5 years low resolution, high resolution truth. And we want to correct the statistical biases of generative models. And the setup is this. We train 2 set of generative models. The first one is trained on 25-year low resolution snapshot. So we assume we have enough input samples, and we train a flow matching model on the 25 years low resolution samples, and then we draw as many as we want. And then we use the very same eta learning map we trained as in the last example. We push all the samples we draw from the low resolution flow matching model into the eta map and get the super resolutive version of them. And we plot the statistics of them. And the key point is the eta map is trained with only 0.5 years of high resolution snapshots. And then we want to compare this to what? To a flow matching model trained only on 0.5 year high resolution snapshots. We train this and we draw as many as we want. Actually, the same amount as what we drew in the same in the first set of a flow matching model. And then so here we only do sampling because it's already high resolution, and we obtain 25-year raw HR snapshots, sampled raw HR snapshots, and we compare the statistics. And here, each of them is an independent sample of them. I'm just to show you that when you train, this is the eta corrected samples. When you train flow matching and you draw low resolution samples, push it into in the eta map, you get snapshots that look like real climate. So again, there's no spatial consistency enforced in there. It's just statistical. But then if you look at the PDF, okay, this is they're manualized here. Let's go through them one by one. The solid line is a high resolution ground truth. That's the same as before. The square dotted line is the low resolution ground truth. So this is this guy, the 25-year low resolution ground truth statistics of that. The triangle dotted line is the low resolution generated samples. So you draw 25 years of samples from your flow matching model after it's trained on the ground truth. You see, you don't reproduce the ground truth statistics, but it's close enough, I would say. And the rhombus line is again the training of the high resolution snapshot you're using. And then this guy here, the circle dotted line, is when you train your flow matching model on 0.5 years of data, and then you draw 25 years worth of samples, you plot the distribution. You see the tail is very off because you're only training on this, and for anything you get beyond this guy, like beyond this, what you have in the training data, I would argue is probably noise. So this is this line, and the last line is our eta learning corrected samples, the statistics of the eta learning corrected high resolution samples. So the input of this guy, this star dotted line, are the samples of the triangle dotted line. So we input those samples, and we get into the eta map, we get those samples. So you see the tail is lifted off here. Oh, sorry, is lifted up a little bit here. That's because in the eta map we have the information for the tails. We enforce the information for the tails, so you get a little bit of those. You get a little bit of lifting up, and that's important. I'm showing you an extra figure here just to give a sanity check that generative models actually suffer from data limitation. So what I did here is I increased the amount of training data model by model, 0.5 years, 22.5 years, 10 years, 25 years, and I plot the statistics. So you see there's a shifting. There's a shifting in the tail. This is just to validate that generative models actually suffer from data limitation. An important thing is if you train the HR generated sample, you train the flow matching models with even 25 years of training data, you get something, you still don't get the exact statistics. So I would say our result here is pretty solid. And then the last example I want to show you is when we don't have the exact new knot. So what we do here is we hypothesize a generalized extreme value distribution, and then use this for our training instead of the true thing. And we want to see what's happening in the estimator. And this can be meaningful in cases like climate change, again, as I mentioned before. So the results have the same layout: low resolution input, HR ground truth, MSE output, and eta output. Because we are actually hypothesizing a heavier tailed distribution than the truth. So in the result, we see that our eta learning output gives spatially it mimics the MSE output, and statistically it matches the hypothesis we're throwing in the training. So the hypothesized extreme value distribution is in the square dotted line, so it's this guy. And our result is this, again, the red star line. So this is, I would say, is matching it pretty closely. And if you go back to the samples, for the cases where in high resolution data, or in high resolution truth, we don't see extremes, our model are like manifesting the extremes here. So yeah, again, statistical level, you see a match. And with that, I conclude my presentation. And the paper is here. It's on archive. So you're very welcome to take a look at it. And I thank you for your attention.
Thank you, Kai, for presenting the work. Do we have any questions for the speaker?
Hi Kai, Zhang here. I have a question actually.
Yeah.
This is more related to your last slides actually. So basically, I was thinking on the fundamental grounds that the question mainly is how robust is the eta learning to misspecification of the prescribed observable statistics actually, and how do we select the right observable in the first place? Specifically the compound extremes and non-stationary systems affected by climate change. So somewhat you answered in the end, the same type of thing, but yeah.
Okay, when you say robust, what do you mean here? Like, what do you mean, like robustness with respect to
Like, how do you select? How do you select? How do you know this is the right one?
the right distribution?
Uh, I mean basically the right observable in the first place.
The right okay, so you're asking about the map G?
Yeah, yeah, yeah.
Okay, this G in this work, we are assuming it is given. And so basically, whatever you mean by extreme, let's say the height of the wave, we take that as our observable. But then in real physical, like in many physical problems, you might not focus on the observable that really indicate the extremeness. You might focus on something like a precursor, and that we don't have a like that. That's a next step. That's actually something I'm working on right now. Like numerically, if you use different observables, what can you say about it, and how do they differ from each other? And mathematically, can we prove something about whether this observable is the thing we want? And in that's actually a different setup, I would argue, because in that setup, you need one observable or one indicator of extremeness, which is the G we are showing here. But then you want to discuss the observables as well. So that's two separate things. So I would argue, like, for the observable question you're asking, that is currently not yet within the scope of this work. But yeah, I'm working on that actually. We are working on that.
Right, because I was thinking why it is critical, like just was thinking on the back of my mind,
Yeah.
for the discussionary point of view, that AI models often fail to perform effectively on rare extreme weathers, right? Or anomalous events that fall outside of distribution of training samples. So that is the first point I was thinking about, and the second was like climate emulators inherently struggle to reproduce non-Gaussian statistics, the characteristics actually of climate data and including extreme events actually.
Yeah.
So yeah, these were the 2 points actually that was pretty much like fundamentally because I'm not very much aware with the eta learning, to be honest. So these were the 2 points that were fundamentally kind of like disturbing me from the start of the discussion. Yeah.
Yep. I agree. Like for in climate emulators, like catching non-Gaussian statistics is challenging. And even if, as I have commented at the first part of the talk, even when you do have extreme data in your data set and you do ML, you can do diffusion model, you can do something. You need some tricks here to make this thing work. You see the anomalous events. And we are asking, actually, I would argue a harder question. So it's, what if we don't get extreme data in the data set? So that's what we're after. And I think this method can also be used in the case where you do get enough data, but then your model suffers. So you can train a correction, use this as a correction operator.
True that. Agree with you. Agree with you. Yeah.
Does that answer your question?
Yeah, somewhat. It was not an question answer thing, but more of a discretionary point of view that I wanted to hear from you actually. Yeah.
Yeah, for sure. I'm happy to talk more later offline.
Yeah, sure. Thank you so much. Thank you.
Yeah, thank you for your comment. Any other questions?
Can I ask a quick question here? Did you use just the tail of the hypothesized new zero
Yes.
here?
Yes, I only use the tail. Yes.
Okay. So that's very interesting, because if you look at the stars, right?
Yes.
And you don't look at the tail, but you go and you look at the bulk of the distribution. The interesting thing is that the stars approximate the bulk of the distribution better than the MSE, which is based on data. So what this tells me is that the bulk of the distribution and the tail are actually connected. They have some correlation. So just as very quick, if in your regularized term you try to enforce not just agreement with the bulk, but with the tail, but also with the bulk, maybe you will get even better results.
I think so. Yeah. To comment on your first comment, the reason why you see this, I also thought about this when I saw the result. The reason why this is aligning better in the bulk is because if you see the MSE, it has it's a lifting up a little bit in here.
Yep.
But then it decays down in here. But then, although we are only correcting the tail in the eta learning,
right,
density, it has to be a density. So
right,
it has to integrate to 1. So you can, like, if you have a lifted up density compared to the MSE, but then you still have the same bulk, that would not do density. So that's why I have a little, this is, and for this particular problem, getting the bulk down a little bit aligns better with the ground truth. But I don't really know if this is I wouldn't claim this is a property of eta learning. It's just like it happens in this example that
I don't think it's a property of eta learning. It's just for me, it's just a sign that the bulk of the distribution and the tail should probably be used both when you try to do the regularizer. Because if you do just data for the bulk and Wasserstein distance for the tail, maybe you are decoupling things in a way that you should not. Maybe there is more information there that you can exploit.
Yeah. The reason why I didn't use the bulk here is because in the setting, we are already assuming that we have some, supervised learning labels. And, I want to see how supervised learning, how far it can take us. So that's why I didn't. But I really
but the red stars are considerably better, even far away around, what is it, around, let's say 100, right? You see, it's much closer to the blue than the green one.
Yeah.
Okay. Thank you. Nice work.
Thank you.
Thank you. Do we have any more questions for the speaker?
I have one quick question. Thanks for nice talk. So I'm just curious that this kind of eta learning can be applied to any physics-informed loss, not MSE or inverse problems.
Absolutely. Like if you look at the paper, the way we wrote it is using general loss. But then, like when we do the experiments, we're assuming MSE. So the MSE, you really should think of it as a supervised learning loss. So it doesn't have to be MSE. Yes.
Thank you so much.
Yeah. just to advertise the paper a little bit more. But yeah.
Do we have any further questions for the speaker?
I thought the paper was published in PNAS, right?
It's we submitted revisions. It's minor revisions, so we are pretty positive on the prospect, but it's not been accepted yet.
Okay, all right. Good luck, anyways.
Yeah, thank you.
All right, in that case, I would like to thank both Kai and Yinling for taking their time to present their work. And I'd like to close this week's seminar and hope all of you have a good weekend ahead. Thank you.
Thank you.
Bye-bye.